Okay. In this problem, we're going to be calculating the escape velocity of the moon. So, in other words, how fast, when you're on the moon, how fast do you have to, shoot something away from the moon such that it never comes back? Okay? How do we do that? The way we're going to do that is we have to say, all right, what is our total energy? Our total energy is going to equal our kinetic energy plus our gravitational potential energy. So, first of all, kinetic energy, this is pretty easy. It's just 1/2 mv squared. Our gravitational potential energy is negative gmm over r. But you remember, why is, I'm going to kind of do this in red here. Why is this negative? Let's think about that for a second. If this is a planet, in this case the moon, then how far away do we have to get before our gravitational potential energy is equal to 0? Where is that? Well, it turns out that from this equation here, the meaning of it states that when you're at infinity, that is when your gravitational potential energy will be 0. Because if you look at the equation, negative something gmm, that's all going to be positive, divided by infinity, well, that's going to tend to 0. So unlike gravitational potential energy when we deal with things on the surface of the Earth, where we say, yeah, the ground, sometimes you do things where you say the gravitational potential energy is mgh. Now what you say then is you say the ground is 0, and so when something goes up, it has a positive gravitational potential energy, and if it loses altitude, that's a loss of gravitational potential energy. But the equation we always used to use was mgh. However, understand that for planetary distances, we can't use that anymore, and the reason we can't use it anymore is because g is not constant. It's changing. And so therefore, that is the reason why we have to use this equation. Negative gmm over r is the gravitational potential, and it's the change in gravitational potential which gives us the amount of energy. So, question now becomes, what does it mean to have a big negative value, let's say at the surface of the moon or at the surface of the Earth? Well, what I like to relate this to is the concept of being indebted. So, let's say, for example, you're indebted to the bank. That means you owe the bank money. That means your balance is a negative balance. The only way you'll be free is if you have a total, say, net worth of 0, in which case you don't owe any more money. Same situation here. If your total energy is equal to 0, you're free. Okay, you're free of the amount of energy you have to pay the Earth, or the moon in this case, to get away. All right, so how would we make our total energy equal to 0? Well, our total energy is equal to our kinetic energy, 1/2 mv squared, plus our gravitational potential energy, and that is all going to be 0. So if we want to solve now for v, we can just say 1/2 mv squared is equal to, now the negative becomes a positive on this side of the equal sign, And we can cancel that m and that m. Those are the same two m's. And we can take the 2 and put it up there and take the square root to solve for v. So now it just becomes 2gm all over r. And that is the escape velocity. Now, I've already calculated this out for the Earth. V escape at the surface of the Earth is about 11.2 kilometers per second. Okay, so in other words, if a projectile travels at 11.2 kilometers per second on the Earth, it's not coming back down. But let's just try it quickly for the Moon. I'm curious what it is. So let's go square root of 2 times 6.67 10 to the negative 11 multiplied by the mass of the Moon, which is 7.4 times 10 to the 22 kilograms, divided by the radius of the Moon, which is 1.74 times 10 to the power of 6 meters. And when we plug that through our calculator, we're going to go 2 enter 6.67 EE negative 11 times 7.4 EE 22 times. And then we're going to go 1.74 EE 6 divided by, and we take the square root, and we're going to get 2.38, okay, or 2,382 meters per second, or 2.38 kilometers per second. Okay, so if on the Moon, if something travels that fast, then it's not coming back to the Moon. Well, hope you enjoyed the video. See you next time.